Okay. Let's get started. I don't really have any major announcements other than the fact that class is canceled on Wednesday because I'm going to be in the great state of Iowa. I'm making a presentation at SSAB Americas, which is a big steel mill out in Iowa. So I'm actually tomorrow I'm leaving Huntington and flying out to essentially going to Davenport, Iowa. I'll be making my presentation in the morning and flying back. So I'm going to have an intense couple days coming up. So if I'm a little scattered on getting back to email, just bear with me. So lectures canceled on Wednesday. You do still have your meeting minutes due on Wednesday on Blackboard. Just make sure you keep up with that. Here this weekend I went and posted, I think it was like the next 5 or so weeks of meeting minutes. So like the meeting minutes are due Wednesday at 5 o'clock. So at 5 o'clock, week 4's meeting minutes is going to deactivate, and week 5's meeting minutes is going to turn on. And I've set that up for the next, like, I think it was like 5 weeks. I got up to like week 9. You have to manually do each one. You really can't copy it. So I just, or you can't, it doesn't work as well. So I just, you know, did a little bit of catch up. Everybody okay on that? Okay. So what I want to do today is I want to explain a little bit on live loads because, like for instance, one group in here has already decided to start breaking out some software for the use in their design, and I think so. You're using the LEAP package, and I think already you're finding that if you're using LEAP software bridge design, which is fine. I think it's an absolutely wonderful package. But one of the things I think you're finding is that there are some terms that maybe if you messed with it before, you didn't understand, and now you're actually kind of starting to understand a little bit. Like when it said sacrificial wearing surface on the deck, like what is that? Now you understand what that is. But real quick, when you start looking at the output, and I'm using LEAP as a for instance, but this is really the case with a lot of the a lot of these types of programs. You're going to start to see like moments and shears and outputs and stuff like that, and it's going to seem really intimidating. And hopefully today I sort of removed some of the mystery associated with this output. Some of this lecture I think you're going to some of it you're going to recognize, some of it not, and that's fine. But I think after today, you'll feel a little better. So let me skip ahead a little bit. We talked a little bit about bridge loads. Remember, we split them up into dead and live. Transient. I'll skip over the code a little bit. Okay, right here, we spent the majority of the last couple days actually just on these two slides, on DC and DW. Now, does anybody have any questions on DC and DW? I think that's pretty straightforward stuff, right? It's literally just, you know, we performed what we call in the world of structural engineering a load takedown. So you're essentially one by one just counting up all the stuff that's put on the bridge and converting it into a structural analysis load model that we as structural engineers can use to say, okay, what are the moments, what are the shears, deflections, et cetera, et cetera, et cetera. Okay, that's dead loads. Live loads are a little different. Okay, now, you know, we need to design bridges for vehicular loads, but it should be noted that cars, and I say cars, and I mean, like, I drive a Hyundai Elantra. Like, my car, bridges don't really give a damn about my car. You know, they get that for free, okay? By vehicular loads, what I mean are exclusionary truck loadings, so heavy truck effects, okay? Now, when we're talking about vehicular loads on bridge that produce significant impact, the word exclusion vehicles mean things like short-haul vehicles, concrete mixers, things like that. Why do I have concrete mixers twice on this slide? I have absolutely no idea. Tanks or something like that, I don't know. So the vehicles that produce worst-case extreme effects. I don't want you to confuse that with extreme events, just, you know, significant loads. Now, do we have to design for every type of vehicle that's on the road? And the answer is no, okay? Now, what ASTRO has done is AASHTO has produced a live load model, and what that live load model does is it simulates the effects of extreme loading on highway bridges. Now, the model is a little funky, but statistically, what it's intended to do is represent what's really going on. So you take all the, to keep it simple, you go out, you monitor weigh-in motion data on highway bridges and whatnot, and you collect all the data of what are the maximum moments that bridges are seeing, and what are the maximum shears that bridges are seeing, et cetera. And then you try and develop, okay, well, what is this load model that we can develop that will mimic what you're getting in the real world? And that's this. So I don't want you to call some trucking company and go, hey, how many HL93s you got out there? An HL93 doesn't exist, okay? It's not a real vehicle. It is a mathematical representation of the maximum force effects that we're seeing on highway bridges, okay? So it's not real. This is just a model that we are using, okay? Before, what we used to use was just the truck and the lane load, and I'm just keeping it simple. But before, we used to use just the truck and the lane load model by themselves and take the worst case of either of them. Well, what we kind of do today is, instead of taking, either or, when it comes to the truck and the lane, we sort of combine them. And what you see here is sort of a graph of before and after. So what this is plotting is what's called moment ratios. And the long and short of it is this is the ratio of what the structural engineer would, and I'm quoting, guess what the moments and shears are. I mean, keep in mind, when you use the code to predict live load, force effects, it is an educated guess, if you will. So what you're seeing here on this axis is the ratio of what the engineer would guess versus what they actually would get. And back in the day when we were just using the HS20 truck, I mean, would there be instances where we'd be seeing, 1.8, 1.9 times the amount of moments? We'd be way under predicting. Now we're doing a lot better. I mean, the scatter is a lot more controlled. So our model that we're using represents real world effects pretty well. Now, that's moments. Here's shears. So you see essentially the same trend. Okay. Now, let's talk about the components, okay? Now, the live load model that we use for highway bridges in the United States, according to AASHTO, contains three components, okay? It contains the truck, the tandem, and the lane. Now, the lane is pretty simple. The lane is just a uniformly distributed load of 640 pounds per foot, or 0.64 pounds per foot. And what that does is sort of represent a constant stream of traffic on the bridge. The trucks and the tandems, those are your more concentrated, heavy vehicle effects on the structure. So let's take these one at a time. Okay, let's talk about the truck. Okay, so I'm pretty sure you all have seen this before, because I showed you this in structural analysis. And we actually did some very basic problems in structural analysis. We'd say things like, okay, here's a beam, here's the truck, produce the maximum force effect at this given location. We did that type of stuff in structural analysis. This is the exact same thing. Okay, now here's the truck. Now the truck is a 3-axle truck, okay? Now this front axle weighs 8 kips. So how much does each tire weigh? 4 kips. That's the load that's applied there. So the front axle weighs 8 kips. The 2 rear axles weigh 32 kips apiece. Okay, now let's talk about spacing, okay? Now the front axle spacing is fixed at 14 feet. The rear axle spacing is fixed at 14 to 30 feet. Now the code stipulates that it is the responsibility of the engineer to vary that axle spacing to produce the extreme force effect. That's not that. Software packages tend to do that stuff for you, so that's not a big deal. But 2, let's talk about this value. Let's say here's a bridge, right? I got a support here, I got a support here, okay? And let's say here's my truck, running on down the bridge, okay? Now if I'm trying, you like my sound effects? All right. Now, if I'm trying to produce the maximum, let's say, bending moment in this beam, am I going to put that at 14 feet or 30 feet? 14, you're going to want to collect those loads close together, lump those loads in the middle. That's going to produce the most bending, right? So it's your responsibility to vary that, but I don't want you to think that that's that big of a deal, okay? There are instances where you fix it at 30 feet. So, and two instances that come to mind very quickly are, one, when we assess fatigue, we are using the same truck, but we are essentially fixing that at 30 feet. So your truck moments and your fatigue truck moments are a little different, okay, because the code stipulates that for fatigue, you're fixing that at 30 feet. The only other instance I can think of where you're going to fix 30 feet are some really odd geometric considerations. Maybe we've got some really odd span arrangements and you're looking at, let's say, negative bending across the pier. It might actually make sense to space that out a little further, but we're talking about some odd geometry. Let's just put it like that. In most instances, especially on a simply supported bridge, you're going to keep that at around 14 feet. Sound good? Okay. Now, the transient load, or the tandem load is meant to simulate some more heavier concentrated loads on the superstructure, and that's just two 25 kip axles that are spaced at 4 feet apart. When you look at truck loads and tandem loads on, let's say a simply supported beam, you're basically just going to take the worst case effect. Now this has a heavier concentrated effect closer together, in terms of space, 50 kips only over a distance of 4 feet. So in terms of, per foot, this has got a heavier force effect, but this is more load. This is 50 kips, this is 72. So you end up just having to run both, and then just on a case-by-case basis, whichever one gives you the worst-case scenario is the one that you run. Does that make sense? Any questions on that? Okay. Now, and this is where I think you all really are going to want to pay attention. So according to AASHTO, the vehicular load shall consist of a combination of either the truck and the lane or the tandem and the lane. Okay, so what you'll do is let's say it's a simply supported bridge. You'll run 3 analyses. You'll run analyses for the truck, for the tandem, and the lane. And you'll get a column of data. Here's the truck moments. Here's the lane moments. Here's the tandem moments. So you'll say the truck and the lane, get a value. Tandem in the lane, get a value. Whichever one's your worst case scenario, that's the one that you're going to use. But there's a couple more caveats that we kind of need to throw on out there. So I'm going to mention the negative bending stuff really quickly because I don't want to harp on negative bending too much. If you all have a pier, we can talk about it, but we'll see. But for negative bending regions, you end up having to do an additional investigation for negative bending across the pier. That's something that the code stipulates. You end up kind of having to use 2 trucks that are straddled across the pier. So let's say here's the pier. The idea is you kind of have 1 truck here and 1 truck here to cause more bending across that central support. The code stipulates that. It only stipulates that for negative bending regions. If you don't have a negative bending region, then you don't need to worry about it. But I have a really clear picture to show you here in a second where that would be useful. So this translates into the following 4 load cases. So the truck in the lane, the tandem in the lane, the double truck in the lane, or the double tandem. And these 2 are just for negative bending regions only. We take 90% because the code stipulates you need to do the investigation, but you don't have to take all of it. You only take 90%. So load cases. So 100% of, truck in the lane, 100% of tandem in the lane, or 90% of double truck or double tandem. And this is only for negative bending regions. If you just have a simply supported bridge, you can ignore slide 19 altogether. Make sense? Okay. Now, those truck loadings are going to be employed when you assess strength and service. Okay, when you do fatigue and when you do live load deflection, you do something a little different. Okay, so for fatigue, okay, so this is what I was mentioning earlier. You use the truck, but you use the truck where the rear axle is spaced or is affixed at a constant distance of 30 feet. So this is where I was saying your truck moments and your fatigue truck moments. Let's that rear axle at 30 feet. So the moments are a little different, a little less. When you assess, so one thing you do fatigue, it's just the truck, no lane and no tandem. And again, if you think I'm throwing a crazy amount of details at you, I am, but I got a really nice summary couple slides at the end. When you assess live load deflection, So bridges have not only must meet strength requirements and fatigue requirements and all that, but there's an optional check that says if your owner so chooses, they will impose a limit just on straight deflection. But every owner in the country does that, so it's not very optional. It's pretty much you have to do it. So there's the design truck, or 25% of the design truck plus the lane. Okay. So everybody okay on that? I mean, I know it's a lot to swallow, but in the end, there's, like I said, there's a pretty nice summary. Everybody okay with that? Now, you'll like this question. What's it like driving generally across roads in America? I mean, is every road in America the smoothest road ever? What do you tend to hit every now and then when you drive? Grand Theft Auto or something? What'd you say? You said potholes, right? Exactly right. I mean, potholes, what's that? I want to talk about potholes, all right? Potholes are a real thing, and they cannot be ignored, okay? Now, I'm talking about potholes, but in generality, what I am really talking about is surface roughness of the road, okay? There is a presence of some degree of surface roughness on the roads and bridges that we drive across on planet Earth. Can't avoid it. It's reality. Now, if you're driving, let's say, a cement mixer or a short-haul vehicle or a cement mixer. I said it twice because I wrote it twice on the slide. But if I drive one of those and I hit potholes, or if I encounter surface roughness on the road, what does that mean for the bridge? We're getting, and you all use the exact right word, you're getting what's called an impact force. In other words, okay, if I stand on this table versus if I jump on this table, would you agree that the force effect on the table is worse if I jump on it than if I just softly stand on it? Do you agree with that? Especially if I'm driving and I hit potholes, there's going to be a boom, an impact force, okay? In the code specifically calls that a dynamic load allowance, but the abbreviation is IM because these are commonly called impact factors, okay? Now, there used to be this really empirical equation that you would use to compute impact factors, but now it's really simple, okay? So when you're performing a load analysis, okay, here's the deal. When you're doing strength limit states, service limit states, extreme event, all that stuff, you use an impact factor of 1.33, and you only apply it to the vehicular component of the load, the truck or the tandem. The only one that's a little unique, or the only ones, is when you use the fatigue limit state, you use joints, you got to bump it up a little further because they're experiencing that direct impact. Does that make sense? Okay, so this is what I was talking about if you want a nice little summary. Okay, so your load cases are as follows. So for strength and service limit states, you have, okay, you'll run a truck analysis, okay? And from those, you will compute some cases. So case one, you'll say, you'll have columns, let's say in Excel. So case one, you'll take 1.33 times the truck, and then add that to the lane, and then that'll give you a case. Case 2, 1.33 times the tandem plus the lane. So 1.33 times the tandem column plus the lane. That'll give you a case. Let's say case 1 and case 2. You'll take the worst case effects from that, and those will essentially be your live load moments and shears. Now, if you combine that with your dead load moments and shears, there's your analysis. Now, you've got MU, compute VMN, and if VMN is greater than or equal to MU, it's funny how you just designed a bridge. Does that make sense? Everybody okay with that? Now there's a couple unique ones, the negative bending ones, the ones that frowny face over the pier. Don't worry about that if you don't have a pier. Fatigue limit states, just take 1.15 times the fatigue truck against, again, all these like 1.15, 1.33, those are just the impact factors, okay? For live load deflection, 1.33 times the truck, or 25% of the truck plus the lane. All right, this slide I would maybe put a big star on when you start doing some calculations. That'll be a good slide to reference. And when you look at output from a software program, from whatever program you all decide to use, whenever you look at that output, hopefully then it makes a little more sense. Does that make sense? Okay, any questions? All right, now what I have done is just sort of essentially vomited out a bunch of specifications and code provisions and load cases and whatnot. That's great, but I'm sure some of you are like, okay, what the hell am I supposed to do with this? Okay, so what I've decided to do is I want to talk to you a little bit about structural analysis on bridges, and particularly live loads, because live load, I mean, dead loads is just, when we did DC1, DC2, like we got DC1 where we get like 1,200 some pounds per foot or something like that. Well, if you got a beam and you got a uniformly distributed load, I hope to goodness you all can compute moments on it. If you can, I failed as a structural analysis professor. But the live loads, that's a little funky, okay? Because live loads, I mean, you're taking a live load and applying it to a three-dimensional system. So let's say this table is my bridge, okay? What we've got to do, and let's say here's my truck, okay? What we've got to do in the world of bridge engineering when it comes to loads is we got to figure out two things. The first thing we have to figure out, if here's my bridge, is we have to figure out where to put the load this way, okay? Like if I'm trying to maximize bending moment on this table, should I put it right there? Maybe I should put it right there. Maybe what I should really do is put it right here, smack dab in the middle, right? Now, in order to determine longitudinal placement on a bridge, and that's what I mean by say longitudinal, along the bridge, in order to determine that, I need to use the theory of influence lines. Y'all remember that? Okay, so that's where influence lines comes into play, is to determine longitudinal placement of a load. That's longitudinal placement. What about transverse placement? Over this way, over that way, in this direction, okay? That is where live load distribution factors come into play. They basically tell you how much truck goes on beam 1 or beam 2 or beam 3. That's where live load distribution comes into play. And it's not difficult, but if you've never been exposed to it and you start pulling design examples off to the internet and you go, what the hell is this? Now, that's kind of the idea, is I want you to understand that. Does that make sense? Now, some of this I'm going to go through quickly because I know you've seen it before, and I know you've seen it before because I taught it to you. Now, when you analyze bridges for dead loads, it's pretty straightforward. Build your analysis model, apply the loads, and do it. Simply support a beam, uniformly distributed load. If you can't draw a shear diagram or a moment diagram from that, I failed as a professor. But live loads, it gets a little more complicated. Now, we have tools that we can apply to make that a little simpler, specifically live load distribution factors and influence lines. And I'm going to talk about influence lines first. Now, I know it's been at least a year since you all have seen this, so just to make sure everybody remembers what an influence line is and how you construct it, you start off by identifying a key point of interest on the bridge. So a key point of interest is like a support reaction, a shear at a given point, a moment at a given point, etc. In bridges, we tend to identify those key points of interest as what we call 10th points. That's very common within bridge engineering. So what I mean by 10th points is that if you have a 100-foot bridge, for instance, you will determine moments and shears at 10 foot, 20 foot, 30 foot, 40 foot, 50 foot, 60 foot, 70 foot, so on and so forth, at every 10th point. So if it's an 80-foot bridge, 8, 16, 24, 32, blah, 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 and so forth. Make sense? Okay. Now, let's just make sure we all remember this. So you construct an influence line by taking a 1 kip load and moving it across the structure. So if I take that unit load and I move it across the structure, and as I move it across the structure, let's say I'm recording, the reaction at A. So if I put it smack dab in the middle, A is a half and B is a half, so I plot a half, and I keep doing that, I get an influence line that looks something like that. Everybody remember that? If you have a statically determinate structure, remember influence lines are always linear, okay? Now, Influence lines also graphically illustrate where to apply loads. You know, for instance, if I've got my HL93 truck and I'm trying to maximize the reaction at A, the influence line does two things for me. Number one, it tells me graphically that my largest influence is over here. So lump that truck all the way over there if you can, all right? And second, it will allow me to directly perform the structural analysis, because all I have to do is take 32 times that ordinate, 32 times that ordinate, 8 times that ordinate, sum it up, right? Okay, so the maximum reaction that I can get at support A from that truck is about 63.6 kips. Sound good? Okay. And we just use that process to do shear and moment influence lines. Same thing, just pick a spot of interest and follow the same procedure. Now, I do want to show you what influence lines look like for indeterminate structures. Now, the structure will divide it, and this is how software will do it. The structure will divide the structure into tenth points. So that's what the software will do. So this bridge, you'd have a section that's cut at 9 foot, 18 foot, 27 foot, da-da-da-da-da-da. And for each of the points, an influence line is drawn, okay? So these are what those influence lines would look like on a structure like this. So this is an influence line at 9 foot, 18 foot, 27 foot, 36, 45, 54. Now, these are curved influence lines. They are curved because the structure is indeterminate, okay? If the structure was determinate, they would all be straight lines, but it's not determinate. And so on and so forth. And so on and so forth. And then the pattern would continue the other way. Does that make sense? Okay. Now I want to take a look at that influence right here. So this is the influence line at 36 feet, or 0.4 span length, so 0.4 L. So everybody okay with this pattern? All right. Now, because the influence line has negative values as well as positive values, I mean, we got a negative bending region, we got a negative ordinate over here, positive ordinate over there. Because of that, we have potential for positive and negative bending at any particular point. This is sort of something you got to get used to. We don't, when we talk about loads in bridge engineering, you'll hear the term envelope mentioned quite a bit. We don't really care about moment and shear diagrams in this world, because at any given point, you can have a maximum positive force effect and a maximum negative force effect. So instead of talking about moment and shear diagrams, we're talking about moment and shear envelopes. Okay? Does that make sense? Because at any given point, you know, for the live load, you have positive and negative effects. Take a look at this. Now, here is our influence line for maximum bending at 0.4 L. I propose that that is where you should put the truck if you want to get maximum positive bending at that location. But if you want to get maximum negative bending at this location, put the truck there. Because what's the bridge going to do? Well, let's see. What are we going to get? We're going to get sort of a smiley face bridge here, frowny face over there, right? Make sense? So would you agree that at any one point you can get a maximum positive value and a maximum negative value? Everybody okay with that? That's where you would put the lane if you want to get maximum positive effects. Remember, with distributed loads, you put them wherever you need that force effect, right? So I propose it to get maximum positive bending, put it there. Maximum negative bending, put it there. Make sense? So when we perform analysis for live loads, we will get envelopes. Those envelopes will probably look something like this. Okay? So let's take a look at this. Okay. So what I have here is I have here a series of columns. This is a very common output that you would get out of a program like Leap or any product that does any type of bridge analysis. Okay, so what we've got here over here in this column is we've got the spans being divvied up into tenth points. So 1.2, 0.3, 0.4, you can see so on and so forth. Now let's take a look at the truck columns. So the truck columns. You can see I've got a series of positive values and a series of negative values. Because at that particular point, so for instance, if I look at 0.4L, which is, from those previous slides, this is the maximum positive bending moment I can get out of the truck. This is the maximum negative bending moment I can get out of the truck. Does that make sense? Because the truck can smiley face and it can frowny face. Okay? So what you would do from here on out is you would say, all right, let's go into my Excel sheet and maybe do something like case 1, positive, negative. And then, so you'd have a column of data here and a column of data here. And what you would do is you'd say, all right, for this first value right here, what I would do is I'd say 1.33, let's say, times the truck plus the lane. And then 1.33 times the tandem plus the lane. And then just drag that down. So, you include all of these values and so on and so forth. Does that make sense? Is everybody okay with that? It's fine. If you got a question, please, Sure, yeah. That is exactly right. You won't have any negative bending moment, but negative shears. It's very possible to have negative shears. Now, do they matter very much? Not really, because it's just symmetric and it's flipped, but you can have negative shears. But you are right. If you were to strictly run a software analysis on a simply supported bridge, these would all be zeros, and all be zeros, and all be zeros. You are exactly right. I'm glad somebody asked that. I was honestly kind of waiting for somebody to ask that. And yeah, specifically, if you just looked at raw output, it would just say zeros. Yes? No. Let me say this. You are bringing up an interesting point. All this stuff that we're talking about here is only concerning placement in this direction. We haven't yet talked about placement in this direction. In order to assess that, what we have to do is utilize what are called live load distribution factors. And live load distribution factor equations change depending upon if you're looking at a steel I-beam bridge or a concrete T-beam bridge or a steel box girder bridge or a concrete or whatever, So does this change? No. But does your transverse distribution change? Yes. Okay, I don't want to give you just repeat the same answer, but let me say this. When you compute live load distribution factors, you are taking into account girder spacings, overhangs, slab thicknesses, and those types of parameters, and girder stiffness, okay? You're taking into account those parameters when you do that. Do you see what I mean? Yeah. So what we're going to do is this, okay? So ultimately what we'll do is we would get, let's say, a case 1 and a case 2 and case 3 and determine our governing values. Sound good? Okay. When you get your governing values, those are still what we call undistributed. We haven't taken those values and say, okay, 30% goes to this beam, 40% goes to this beam, et cetera, okay? That is a completely separate calculation. But what we would end up doing is we say, okay, let's say I get a governing value, but my distribution factor is 0.4. So take those values, multiply them by 0.4, and what you're doing is converting just moments and shears on just some random old beam to how much of those moment and shears can we expect on this beam or that beam or that beam. You see what I mean? I'm not trying to give you the same answer that I just gave you, but what I am saying is all those transverse dimensions, slab thickness, girder spacing, all that, they are taken into account when you compute distribution factors. Does that answer your question? Well, I mean, okay. Does anybody else have any other questions? This is kind of important, and I want to make sure that you all understand this. Yeah. Yes. Yeah, exactly. See, influence lines are sort of an inverse of shear and moment diagrams, if you remember. Like when you're doing a shear and moment diagram, the loads sit still, but your plot is continuous across the entire span, right? When you do an influence line, your point of interest sits still, but the loads move, okay? So an influence line will allow you to determine the worst case position anywhere on the bridge, but its limit is that it will only give you the worst case scenario at that point. So if you want an accurate representation of the moments and shears across the bridge, the thing that sucks about it is you just kind of have to draw a bunch of influence lines. Now, do you draw an influence line for every foot? You know, I mean, if you've got a bridge that's 150 foot long, that's 150 or 151 influence lines, right? Instead, in most cases, the bridge engineering community accepts that if you divvy up the bridge into 10th points, that's close enough for government work. Because you could take a theoretical bridge, divvy it up into 10th points, do the analysis. Then divvy it up into 100th points, do the analysis. You'll get a different answer. It won't be that much different. You see what I mean? There is a point when you, in practicality, you just sort of go with it. And 10th points is generally accepted within the bridge engineering community. And let me say this. If I have a really long, singly supported, if I had a 300-foot bridge, something like that, something really long, I'd probably do 20th points or something a little more specific just to make myself feel better. Because those are some serious spans. But for a regular run-of-the-mill 100, 120, 150-foot bridge, something like that, 10th points are fine. Yeah, and you're bringing up another point. What I am presenting, in the end, okay, the load provisions that I presented, you know, those are code specifications. Those don't change. But if you have a horizontally curved, skewed bridge at different elevations, you've got all sorts of odd span arrangements, we're taking lines and, you know, the little triangle support and the hinge and the roller. Those are very simple analysis models that we can do by hand. But if you've got a bridge that's got significant horizontal curvature, significant skew, and additional geometric complexities, it's time to break out the full-blown 3D, you know, finite element software and do it for real. You know, like three-dimensional moment and shear analysis. Like, do it for real. This is simplified because we're dealing, you gotta understand, most bridges that bridge engineers design are somewhat simplified, you know. When you've got the really complex bridge, you gotta do the really complex analysis. Like, that's just, you have to. For what we're talking about and for what most bridge engineers deal with on a daily basis, it's not really that necessary. I mean, the only times that bridge engineers do that type of analysis on a geometrically simple bridge is like in a research setting when they're trying to research some advanced effect. Like, I do it a lot, but I'm a researcher. I'm trying to, you know, understand that behavior a little more accurately, but not for regular run-of-the-mill design. So, does that make sense? What time is it? Okay, let me at least very briefly mention live load distribution factors, just so you all kind of have an idea of what they are and what they represent. I might go through an example with you all sometime in the not too distant future. I did not, oh, that's the one I just had. I did not post these, but I will. See, I did my PhD dissertation. The topic of that dissertation was the development of a steel bent tub girder for short span applications. That was the topic of my PhD. The topic of my master's was live load distribution factors. I can talk about live load distribution factors all day long. I love the topic. In fact, there's a point when you might have to say, Dr. Mike, we get it. Shut up. I'm kidding. But live load distribution factors conceptually are a very simple, straightforward tool, but they are incredibly useful. I think there's plenty of room for improvement. in terms of the ones that are currently in the spec. I think we could do better. There is always a healthy balance between coming up with better equations, but also coming up with equations that, while they might be better, they're also more complicated. See, the purpose of a live load distribution factor is to take a three-dimensional problem and collapse it into a two-dimensional analysis. Okay? Again, a bridge is a three-dimensional system. If we can collapse it into two dimensions, that's what we want. Because when you all learn structural analysis, as does every civil engineer when they learn structural analysis when they're in college and use it throughout their career, they're learning it in a two-dimensional setting. I mean, a shear and moment diagram, that's a two-dimensional problem. You know, you have a x and y axis, and here's your shear and moments. We love 2D analysis, because it's easy to perform. We can do it any day of the week. The way that we collapse a three-dimensional bridge problem into a two-dimensional analysis is with live load distribution factors. And a live load distribution factor is essentially like, here's what they are, okay? So what I do is I take moments and shears from what I'm calling a line girder analysis. A line girder analysis is, long and short, that's what I taught y'all in structural analysis. You know, beam, loads, shear, and moment diagrams. It's the beam is just a line, right? That's what a line girder analysis. So what you all did in structural analysis is line girder stuff. What I would do is take those moments and adjust them. I multiply them at live load distribution factor G. And what I do is when I do that, I get quote-unquote real-life moments and shears acting on a given, moments or shears acting on a given girder. I say quote-unquote because these are approximations. It's an analysis model. It's not perfect, okay? I want to talk a little bit about factors. By and large, the most important parameter regarding live load distribution is the girder spacing, period. Used to be that girder spacing, like what you would do is you take a beam or a bridge, you say the girder spacing is 10 foot, you take it and just divide it by a value. Like say 10 foot, divide it by 5 or 5.5 or what have you, and bam, there's your distribution factor. And the reason why is if you think about it, the farther apart beams get, the more they are responsible for. Think about that. If I put a truck on a bridge, if I got beams that are spaced really, really close together, well, that one truck gets divvied up by not just the beam that it's on, but by the beams that it's next to. Truck on one beam, well, that one beam's taking up quite a bit of that load. Does that make sense? So by and large, girder spacing is the most important parameter, period. But it's not that simple. I mean, bridges are complex three-dimensional systems, and there's a lot more going on than just girder spacing. Like what you'll find is that the moments on a particular beam will go down if the beam gets longer. That seems a little weird, but that's the facts because it's not just two-dimensional. It's three-dimensional. Loads go this way as well. Okay? So there was a study that was done by Ensign and Associates out in Sacramento back in the 80s, and they did a boatload of analyses to try and come up with better approximations and better equations for live load distribution factors. And these are the ones that are present in the spec. So like this is just a comparison of distribution factors before and after. So to give you kind of an idea, so all right, so what you're seeing here, this is what's called in the world of statistics a QQ plot. So the idea is if you look at a given point, okay, this given point like right here, this is what the software that they were using predicts. This is what their approximate equation came up with. Now you can see a much tighter correlation over here on the right than over here on the left. Because everything on the left is what AASHTO used to use. This is what we use now. So you can see there's a much better correlation. The equations that we use now predict those moments and shears a lot better than they did back than just this. You know, what you end up finding a lot in the specifications, and this is a shame, but it ends up happening, is some researcher will do some study and develop some computational model that's really simple. The problem is that computational model that worked out very well, it worked out very well in this small little bubble with this very small little range and what have you. Like these values of take S and divide it by 10 or S and divide it by 5.5. They for a really small range. But then what happened is When they wrote the spec, oh, we'll just use it everywhere, you know. That's great. But then when you actually start doing the analysis, you find you've been over or under predicting your moments and shears, and you've been designing for this for years. So that's where these equations come into play. I'm not going to go through all the technical details behind their development and the actual equation. We're running out of time. But I will mention that it's not a very laborious process, but it is sort of a step-by-step process that we will be dealing with, that we will investigate step by step, and we'll do it on Friday, okay? Because Wednesday I will not be here. I know I've presented a lot of tech and a lot of details, but this is the type of stuff that when you research it on your own, it's like, what the heck is all this? Any questions? Is your projects going well? Everything going great? Any questions about anything? You tell me. See, this is one of those classes where I could go up here and talk all day, but in the end, you still have submissions due. So you tell me. I'm perfectly fine to get along with. Do you want to continue discussing this on Friday, or do you all want to take a break from lecture on Friday and actually just discuss your projects and actually give you all a chance to come in and ask whatever questions you want? We are going to do that. We can do it Friday, or we can do it sometime next week. It's up to you all. Yeah. That's fine. That's fine. I do want to give you all the chance to just come in and go, okay, what the heck's going on? That's fine. And that's fine. Y'all want to do that next week? All right, let's do that next week. So I'll continue this discussion on Friday, and we'll just next week keep on trucking. That's all I got, guys.